Hello friends, I am Dr. Rahul Kaushik. Today we are going to cover another important topic of our syllabus, fourth unit of syllabus, which is production, industrial production, estimation and utilization of phytoconstituents. Today we are going to cover another important phytoconstituent, which is Vinca alkaloids. Vinca alkaloids, as such, it is a group of alkaloids. In the image, if you can see that it is a group of alkaloids which contains a number of alkaloids. Right now we are having vinblastine, vincristine. They are the naturally occurring Vinca alkaloids, and also because of the increased demand for this drug, there are certain synthetic derivatives also prepared by the industries for mass level production of the Vinca alkaloids. The semi-synthetic derivatives of Vinca alkaloids, they are vindacine, vinorelbine and vinflunine. These are the synthetic derivatives of Vinca alkaloids. And if you can see the structure, it is a complex structure which composed of two basic nucleuses. In the orange picture you can see that there is a catharanthine nucleus and there is vindoline nucleus in the green color. Together these both structures, they combinedly form the basic nucleus of Vinca alkaloids. And if we want to classify the alkaloids on the basis of the structure, you can see there are certain functional groups which has to be attached at R1, R2, R3, R4 and R5 on the basis of different different functional groups at these positions. These alkaloid structure, they are classified as vinblastine and vincristine. If you can see here that if R1 is CH3, R1 means you have R1 as this position, R2 is COOCH3, so this should be the COOCH3, and R3 OCOCH3, and R4 is CH2CH3, and R5 is also CH2CH3. In this case you can call the compound vinblastine. Similar case is with vincristine. If R1 is CHO, R2 is COOCH3, R3 is OCOCH3 and R4 is OH and R5 is CH2CH3. So in this way you can classify the compounds Vinca alkaloids with the different names on the basis of various functional groups attached to the basic nucleus of Vinca alkaloids. And you can see the image of Vinca alkaloids. This is the periwinkle plant. Periwinkle, you must be aware with the periwinkle plant. It is Catharanthus roseus, or in Hindi you can you know it with the name of Sadabahar. So this is the plant from where you can isolate the Vinca alkaloids. So if we look at the introduction part of Vinca alkaloids are a subset of drugs, as we have seen in the previous slide that it is a group of compounds or group of alkaloids. It is a subset of drugs which are obtained from the Madagascar periwinkle plant. They are naturally extracted from the pink periwinkle whole plant. You must have seen the Sadabahar plant with the white flower or with the reddish flower, but good quality alkaloid, Vinca alkaloid, they are only isolated from the pink color periwinkle whole plant. Whole plant means it includes the entire aerial part of the plant. So the botanical name for periwinkle is Catharanthus roseus, from which you can isolate the Vinca alkaloids. The plant Catharanthus roseus is belongs to the family Apocynaceae. Apocynaceae is the family from which you can obtain the Catharanthus roseus. There is another name for this Catharanthus roseus. It is Vinca rosea. So when it is Vinca, it is rosea, and in case of Catharanthus we can use the species name roseus, Catharanthus roseus. So chemically, if you look at the structure, they belongs to the, we have seen the basic two catharanthine and vindoline nucleuses. Here we can classify it in the indole class of alkaloids, and physically if you see the alkaloid, it occurs in the form of a white crystalline solid. It is odorless, it is not having any odor, and it is hygroscopic powder. Hygroscopic means it absorbs moisture from the atmosphere. Catharanthus roseus, if you look at the nativeness of the plant, it is native to Indian Ocean island, Madagascar. It is an island in the Indian Ocean, and it is also grown in other part of the world also due to its medicinal value. Since it occurs in the form of a weed in China, so it is widely available, or you can say it is widely used in China in the form of regular teas, like we take the tea in India. So it is common in many tropical and subtropical regions worldwide, including southern United States. If you see the solubility of your phytoconstituent Vinca alkaloids, because we are going to isolate the phytoconstituent from the parent drug, so we should know which solvents we have to use for isolation of the particular phytoconstituent. You can see that the Vinca alkaloid, they are soluble in organic solvents like DMSO and dimethyl formamide. Also, you can see because of its complex structure, it is insoluble in water. So it is water insoluble. If we look at the uses of Vinca, we can see that it is a potent anti-cancer drug, and because of this anti-cancer activity, its semi-synthetic derivatives, they were synthesized, and mass level production, because the demand for drug is increasing day by day, so semi-synthetic derivatives were formulated. It is also having anti-hypertensive and a hypoglycemic effect, along with the disinfectant use. In China, people use this drug in the form of decoction daily after their meal in certain areas where this herb or this herb is commonly used or commonly found. If you look at the cultivation and processing of Vinca, you can see the beds of Vinca here in the pictures. You can see the this is the white periwinkle plant, but we do not use it for the extraction of drug. This is another variety of Catharanthus plant or Vinca plant. This is the Catharanthus roseus, the pink variety of flower from where we isolate the Vinca alkaloids, good quality of Vinca alkaloids. And you can see in the picture also, it is the powdered form of vincristine or vinblastine and other group of alkaloids. So since we are dealing with the phytoconstituent, so we should know what is the mechanism of action with which this drug is going to act in your body. If you see in the picture, in normal mitosis is the division of cells into two parts. So during normal mitosis, we have a number of phases from where a cell passes through, and it finally divides in the form of two cells. So during metaphases, the chromosomes, the genetic material of the cell, it aligns itself to the center of the cell with the help of these spindle fibers. These spindle fibers, they are made up of these tubulin molecules. These tubulin molecules, they stack over each other to form a mitotic spindle, and during the process of cell division, these tubulin molecule made up spindle fiber, they detach or it separates the genetic material into two halves. So the entire chromosome, it is aligned at center, and in this phase, anaphase, which is after metaphase, you can see that the half of the genetic material is transferred in this side, opposite pole, and half of the genetic material is transferred in this side. In this way, cell division occurs normally during the stage of cancer. When we have cancer, so cancer means it is the uncontrolled growth of cells or uncontrolled division of the cells. But when we use the Vinca alkaloids, what happened during the use of Vinca alkaloid? Vinca alkaloid, they bind to the tubulin and they inhibit the polymerization of the tubulin molecules, and when the polymerization of these tubulin molecules it inhibited, it prevent the formation of spindle fibers. So what happened? These spindle fibers, they are unable to form. So in this, here you can see that in metaphase, all the chromosome material, they are aligned at the center, but due to the use of Vinca alkaloids, these tubulin molecules, they are not able to form a spindle moiety like this. Okay, so in this way there is no formation of these fiber like structures which carry the genetic material to the opposite poles, and in this way your cell cycle stops or your cell will not proceed to the anaphase. So this is the mechanism of action with which your anti-cancer drug is going to act in your body. So the cell cycle is arrested in the metaphase, causing the arrest of the cell division. This is the more enlarged view of the mechanism of action of your Vinca alkaloids. In here you can see that this is the microtubule complex, and these are the tubulin molecules which together combine to form this complex. But unfortunately, when we use Vinca alkaloids, what happen? This will form a Vinca bound tubulin dimer, and these dimer they will form a crystalline structure, which is here you can see that paracrystalline aggregate, and they are unable to form the fibers or the spindle fibers which carry the genetic material to the opposite poles. So in this way you can make your cell dead, or you can stop the division of the cell. Moving on to the production. If you look at the production is quite complex, because here we are using a large amount of raw material, but the final material in the form of phytoconstituent we get is very less. So here you can see that we have taken 20 grams of dried and finely crushed leaves, which are extracted 4 times with the 10 liter ethanol. Ethanol here we are using for extraction, and every time we use 10 liter of ethanol. The filtrates of ethanolic extract, or you can say the ethanolic extract, they are then combined, and the solvent is evaporated first in the flash evaporator, because the amount of liquid is too high, amount of filtrate is too high. So we first use the flash evaporator, and then we concentrate the extract in the rotary vacuum evaporator to obtain the gummy residue, and this gummy residue is then acidified with 5% HCl, which is probably 5 liters in this case, and the combined mixture is then washed with chloroform. The gummy extract is then basified with ammonia solution and extracted 3 times with 2 liter of chloroform each time. So in this way you acidify the gummy extract and wash it with chloroform, and then again that acidified gummy extract is then again basified with ammonia, and after basification you have to again extract it with 2 liters of chloroform 3 times. The chloroform extracts we obtain after 3 washings, they are then combined and dried over anhydrous sodium sulfate and concentrated to alkaloidal gum. Again we are getting an alkaloidal gum. This alkaloidal gum is then mixed with 400 ml of chloroform, which is then extracted with 1 liter of phosphate buffer, the pH of which was set at pH 3. The chloroform layer dried over anhydrous sodium sulfate is then filtered and concentrated under vacuum to 60 gram of alkaloidal mixture. So finally from 20 kg we are getting only 60 gram alkaloidal mixture, from where we have to isolate our desired phytoconstituent, which are vincristine and vinblastine. So you can see the procedure. The alkaloidal mixture, that 60 gram of alkaloidal mixture, is then treated with 240 ml of chloroform and 480 ml of petroleum ether. Upon addition of petroleum ether, you get the precipitation of the alkaloidal mixture. So here you can get the precipitate of catharanthine, vindoline and vinblastine. Because we are here in this isolation method, we are targeting the isolation of vinblastine. So you can see that the vinblastine containing fraction, the precipitate of vinblastine containing fraction, which is approximately 20 gram, it is loaded on the flash chromatography column, which contains around 200 gram of alumina. The column is eluted with 70% ethyl acetate, which is prepared in petroleum ether, and around 7 liters of ethyl acetate petroleum ether mixture we have used for this elution. The elutes thus obtained are then concentrated to a gummy extract, which is around 10 grams, and again reloaded on the same type of column, which is packed with 30 gram of silica and eluted with 50% ethyl acetate in petroleum ether. So in this way we can separate the Vinca alkaloid vinblastine from the leaves or from the raw material to the final state. Subsequent elution with 0.5% ethanol in ethyl acetate affords vinblastine rich fraction, which is about 0.6 gram. So it is very important to note here that from 20 kg of raw material we have got only 0.6 gram of vinblastine. So you can calculate easily the percentage yield from this method. Since the drug is very potent, so these extraction methods are further needed to be refined to increase the yield of the fractions. So moving on to the chemical identification of Vinca alkaloids. Suppose you have isolated the Vinca alkaloids, so you have to do preliminary screening of your phytoconstituent isolated from the above method, that your separated compound or your separated phytoconstituent in is vinblastine or vincrystine or any of the Vinca alkaloid. So here we have Van-Erck's reagent. It is a specialized reagent which is specially used for the detection of indole alkaloids, and when you react the Vinca reagent with the indole indole alkaloids, you get the reddish brown precipitate, reddish brown color in the solution. So there are another tests like vanillin HCl reagent, which gives pink color with vinblastine and orange yellow color with vincrystine. So vanillin HCl reagent is differentiating between the vinblastine and vincrystine by its color. So vinblastine gives pink color with vanillin HCl reagent, whereas vincrystine gives orange yellow color with vanillin HCl reagent. Moving on to the, this is the assembly of it is the assembly of a column chromatography. Here you can see how compounds they are getting separated into different fractions. So there is a mixture and it is getting separated. First you have the blue component, then you have the yellow component, and finally you will have the red component of your mixture. So in this way you can isolate a mixture of compound into separate fractions. If you look at the properties of Vinca alkaloids, so they have got the melting point of around 267 degrees Celsius, and this is the image, white hygroscopic powder. The boiling point is not available because there are various varieties or various you can say the various types or various fractions of your Vinca alkaloids. So boiling point is not fixed. Solubility, it is practically insoluble in water, petroleum ether, but it is soluble in alcohols, acetone, ethyl acetate and chloroform. The density is 1.4. If you look at the storage temperature, if you want to store your isolated fraction, you have to store it between 2 to 8 degrees Celsius. It occurs in the form of white crystalline powder, as you can see in the picture itself. Water solubility, if you as we have seen that it is very insoluble in water, so here you can see the solubility in water only 4.46 into 10 to the power minus 2. It means 0.0046, sorry 0.046 mg of drug or Vinca alkaloid is soluble in 1 liter of the water at 25 degrees Celsius. It has got a lambda max of 214 and 259 nanometers. If we look at the separation and identification of the phytoconstituent, you can see we have got various techniques like TLC, HPLC and HPTLC. If you see at the TLC, we have used the pre-prepared or pre-coated plates of silica gel 60 GF 254. The mobile phase for TLC detection, we have used toluene, ethyl acetate and benzene in the ratio of 6:3:1 volume by volume. Flow rate is not applicable in TLC analysis, it is for HPLC analysis. Detection of our spot of Vinca alkaloid was done with the use of iodine chamber, and the slide is or the your plate is visualized under UV cabinet or at high wavelength or long wavelength at 366 nanometer. The RF we got under these conditions, the retention factor we have got for vincristine it is 0.36, and for vinblastine we got the RF value of 0.48. So in this way we can identify, or we can separate, or we can estimate the compound in our drug sample. For TLC analysis, we have prepared the sample by dissolving 1 mg of the extract in 10 ml of ethanol. For standard, we have used 1 mg of vincristine and 1 mg of vinblastine in 500 ml ethanol separately, and we have spotted the samples on the TLC plate, and we have maintained these conditions. And in these conditions, in TLC analysis, we have got the RF value of 0.36 for vincristine and 0.48 for vinblastine. So in this way we can carry out the TLC analysis. For HPLC analysis, we have used the chromolith performance reverse phase column, C18 column here we have used for HPLC analysis. For HPLC analysis, we have used the acetonitrile 0.4 molar phosphate buffer, 0.5% glycol acetic acid, pH 3.5 in the ratio of 21:79%. It means 21% acetonitrile and 79% this phosphate buffer. So under these conditions we can carry out the HPLC analysis. The flow rate here we have maintained for this analysis through the column is 1.2 ml per minute, and 20 microliter injection we have injected in the HPLC. The detector of HPLC machine was set at 254 nanometer, and the UV detector is used for this particular analysis. Under these conditions we have got the retention time for our Vinca alkaloid at 16.57 minutes. Retention time is the time from the injection. It is the time period between the injection of your sample to the reaching of your sample to the detector. So it is the time between it is the time which is taken by the your phytoconstituent to reach at the detector after injection. So for HPLC analysis, we have prepared the sample by this method, where you can see that the leaf powder ethanolic extract is acidified with 3% HCl and defatted using hexane. Aqueous layer is basified with ammonia to pH 8.4 and extracted with chloroform, washed with water and concentrated, and residue is dissolved in methanol, and it is injected in the HPLC machine. So here we have also prepared the standard by using variable concentration of vincristine and vinblastine in the concentration range of 0.25 microgram to 25 microgram per ml of vincristine and vinblastine. So we have prepared the standard plots on which we have spotted our sample. This is the HPLC machine. You can have a look over it. It contains it has the solvent reservoir. Then you have pump. This is the injector. This is the HPLC column through which we have to pass the sample, and here is the detector, and here is the waste. Every component, they are connected with the computer. So in this way, automatically every reading is getting fed into the computer. This is the solvent reservoir, this is the column holder, this is the detector, and this is the sample tray. Moving on to next, this is the HPTLC analysis. Here we have used the pre-coated silica gel plates. Here we have used the mobile phase toluene methanol diethylamine in the ratio of 8.75 is to 0.75 to 0.5. So in this way we have carry out the TLC analysis. Saturation time for chamber is 10 minutes. The total run time is about 25 minutes at room temperature, and we have run the sample up to 8 cm from the point of application. Derivatizing reagent here we have used is vanillin sulfuric acid 1%, and that plates were dried in oven at 105 degrees Celsius. we have detected the vinblastine and vincrystine at 225 nanometer and 307 nanometer for vincrystine, and for vinblastine at 225 nanometer. For the RA value for vinblastine is 0.49 for this analysis, and for vincrystine we have got the RA value of 0.39. In this way you can carry out the HPTLC analysis for your drug. This is the HPLC machine, this is the automatic sampler, this is the developing chamber, here is the chromatogram development chamber. Then you can scan your pictures, then you can visualize the spots, and everything it is getting done with the help of a VisionCat software which is available in the market. Finally, we have to we should know what about the uses of this Vinca alkaloids we are going to isolate. So you can see here that Vinca is a potent anti-cancer drug, and you can see that vincrystine, especially vincrystine, it is used to treat the acute leukemia and other types of lymphomas. So it is a potent anti-cancer drug which is being used in the treatment of acute leukemia and other types of lymphomas. Whereas if you see the use of vinblastine is used to treat the disease like Hodgkin's disease, which is another type of testicular cancer, advanced testicular cancer stage, and it is also used in the treatment of breast cancer. So it is a drug of choice for treatment of breast cancer in advanced stages. Also these Vinca alkaloids, they are used in the treatment of certain kind of blood disorders like histiocytosis. Also they have been used, as we have seen in the very first slide, these Vinca alkaloids, they are being used in a variety of diseases apart from the anti-cancer use. It is also used to treat diabetes, hypertension, high blood pressure, and it is also used as disinfectant. So in this way you can utilize your Vinca alkaloids. If you look at if you look at the brief recap, you can see that we have estimated our phytoconstituent using your HPTLC analysis. This is HPLC analysis and TLC analysis. So these machines or sophisticated techniques like TLC, HPLC and HPTLC we can use for identification and detection of our phytoconstituent in the sample. These are the properties of Vinca alkaloids. We have got a melting point, sharp melting point of 267 degrees Celsius. Then solubility, we have seen it is practically insoluble in water, but it is soluble in alcohols, acetones, ethyl acetate and chloroforms. The density is greater than water, it is around 1.4. The storage temperature for purified vincrystine powder, it is around 2 to 8 degrees Celsius. Then it occurs in the form of white crystalline powder, which is hygroscopic nature, which absorbs water. And here you can see the assembly and functioning of a column chromatography. Here you can see that a mixture came over here in this packing of column, and on the basis of their polarity, on the basis of their affinity toward the stationary phase, the phytoconstituent, they are moving downward. Okay. So in this way you can carry out the column chromatography of any sample. So this is the basic mechanism or basic technique from which you can isolate your phytoconstituent Vinca alkaloid from the drug, from the raw material, and you can estimate your drug in the drug sample. So thank you so much for your patience. In next slide we are going to cover our another remaining topic, which is atropine. We are going to cover the production and utilization estimation of atropine alkaloid, and thank you so much.